Hi, so my name is Sebastian, part of the HetSys CDT with Oscar, so that's why I'm here today. And I'm kind of an early stage PhD student working with Radu, James Brittles, and Albert. My talk today is going to be on data-driven equation discovery, and more specifically relating to thin films, eventually when we get there. So here's a quick overview of everything I'd quite like to talk to you about today. So I want to present kind of how data-driven equation discovery can work with analytical work rather than replace it. I want to go through how a particular method for recovering equations works and some of the results from that, and then some results that we got when we tried to recreate that work before moving on to talk about thin films, why equation discovery is important to people working with thin films. So yeah. This is a nice diagram that shows how data-driven work can hopefully work with analytical work. So a kind of standard way of going about problem solving is that you have a problem, you try to model it mathematically, you then might be able to get a discrete solution if you have, for example, a PDE, and hopefully that can help you answer your problem. So if you're using the data world, I mean, maybe you can't get a mathematical model out very easily, but maybe you have data, observations of like a dynamical system, and hopefully you can discover an equation that can give you a discrete solution or can just answer whatever problem you've got. So they can kind of work side by side, in which you can use equation discovery to help produce discrete solutions that you would otherwise have got from your mathematical model, or you can maybe use a bit of analytical work to help discover equations that can answer your problems. So yeah. So a good overview, what am I actually trying to do? Well, you take solution data or PDE, so for example, this is advection-diffusion, and you try and get a PDE that describes the data well. So this is what we managed to get out using this, for example. So it's literally just data in, produce a PDE that's readable to mathematicians. And there is that need for interpretability. We do want mathematicians to be able to like read these PDEs. There's a lot of adjacent work using like PINNs and neural ODEs, but they don't produce nice readable equations. It's nasty linear combinations of activation functions and such. So yeah. So that's why we're interested in the SINDy method. So SINDy stands for sparse identification of nonlinear dynamics. This is quite a busy diagram, I appreciate, but it's a very good overview of what the entire method is. You basically start at this top left, where you have a dynamical system, lots of observations of it. This is the Lorentz system, so it can be described by ODEs, but it could be a dynamical system described by PDEs. That's one of the beauties of this. You can apply it to both ODEs and PDEs. From this, you need to form a linear system somehow. AX equals B, nothing too tricky. But you can't fit to zero. You need to fix some kind of functional form. So a nice way of doing that is to take time derivatives and set that as your B, your left-hand side. So for example, you take X, Y, Z, and you would numerically approximate the time derivative and form this left-hand side. You then need to pick some functional forms that could represent the dynamics in some kind of linear combination. And then you can hopefully do a sparse regression to identify a system that should hopefully recreate the dynamics. So yeah, it's basically just all built on supervised learning sparse regression. And you pick some functions like x, y, x squared, y squared, that you think might be inside of these governing equations. So yeah. One other thing with this diagram is, notice this is 3 equations. So that's why I've got 3 columns here and 3 columns here. You can do this for single equations. You could do this for n equations. It scales quite well. So yeah, to reiterate basically what I just said and cover the key points, you assume a left-hand side of your equation. You define a basis set, you numerically approximate whatever's of interest, for example, dh dx or h squared. You form a linear system using those approximations, so that's why these theta and b are dependent on x, x being your data, and then you perform a sparse regression on top of that. The reason why we do a sparse regression, we assume that most equations can be described by just a few terms. Like most equations don't include like 100 or 200 terms. So that's kind of an underlying assumption by making this sparse. And by doing sparse regression, that's where you get a lot of hyperparameters coming in. So that can muddy the water and what's actually going on, I guess. So yeah. given that the basis set is quite important, and also your data is quite important in any machine learning application, I'll take a minute just to address these. So you can choose any set of functions in theory for your data set, but you do need to be careful if they are really similar to one another. So for example, if you're thinking of data that's really close to like a mean of 1, h squared, h cubed, h to the 6 all starts looking really, really similar because 1 to the 6 is the same as 1 squared. And you've also got to be careful as well. One of the nice things that can come out is if you have like a sin x function in your basis set and you have a load of polynomials, you might accidentally recover a Taylor series or get competition between those two. So that can be quite nice. So yeah, you've got to be careful of collinearity basically. Are your functions super similar to each other? Throughout the talk, this is a typical basis set that I use for the stuff that I'm looking at. So if I say a typical or a default basis set, that's probably what I'm talking about. It's polynomials, it includes lots of spatial derivatives, does the job. And then sometimes I might even talk about an extended version. So it includes like these cross products, whatever you want to call them. So yeah. And then going to the data set's really crucial. You build your entire linear system based on estimates derived from your data. So it's really important. You need to make sure that everything's active inside your data set. So if you've got two sets of dynamics, but you only ever see one appearing, for example, if you don't run it long enough, if you've got a slow timescale set of dynamics, then you're only ever going to get one thing out. The choice of coordinate system is a nice sub-problem that I won't go into today, but basically how you represent your data can affect how easy it is to get equations out. And you need to be very careful about what's actually in your data. For example, there was a group of people who tried to derive an equation to describe the motion of a pendulum. They took videos of the pendulum and there were shadows in the back of it. So then when they put it into the equation discovery algorithm, it was basically trying to fit the motion of two objects because they forgot to account for shadows existing. So be careful with that. Anyway, these are some results that have come from applying the SINDy algorithm. This is not my work, this is someone else's work. Done a few years ago, and this is what got me excited about using SINDy. It can be applied to a range of PDEs. It can get back the equations with really good accuracy, and it includes some quite complicated PDEs. So the KS equation is one that I like to highlight here because it's got a very high order derivative, and also the KDV is quite important because it's quite impressive that that was recovered when it could be confused for like a linear advection equation. So this was like really exciting and made me think, wow, it can do so much. So yeah, then I took SINDy, I tried to apply it myself and then realized as I go through the papers and stuff that they're just picking hyperparameters that work quite nicely. So I made a few adjustments, including sampling, so that we actually we don't just randomly pick ones that work. And we included a few nice bolt-ons like k-fold cross-validation instead of just a single test train split, which means we also have truly independent test data. So yeah, won't go into too many details there. So yeah, from trying to then recover the results, it worked really well on some basic equations like advection-diffusion. And then once we got excited that it worked on the really basic cases, we thought of some more potentially problematic PDEs. And the advection-diffusion equation was kind of a natural next step. And that one became quite interesting because typically when you do your sparse regression, we would normalize the columns on that big matrix A or theta. But this was a rare example where normalizing actually hindered performance a lot of the time. And quite often you'd only actually get the diffusive dynamics or the effective dynamics depending on your value of diffusion coefficient and advection coefficient. So yeah, it is a really good test bed for making sure that whatever you're trying to apply can actually pick out two sets of dynamics that are quite different to one another. And then we also thought about the linear fourth order case because we saw the KS equation got recovered, so we thought this would be quite simple, but it's really just a good case for testing whether or not you can get high order derivatives back. And if your run goes wrong, it begins to look a bit like this. This is a really good example for seeing what a poor result looks like, because you can see it's minus 900 plus 1900 minus, it's just minus plus, trying to balance it out, trying to fit to the data. So it's a brilliant example of overfitting if you ever need one. So yeah, So we got very excited about all that. And my PhD is more to do with thin films. So I'm going to take a step back and talk about why people who work with thin films are interested in equation discovery. This is a typical setup for a thin film problem, just an inclined plane, fluid running along an inclined plane. It's affected by gravity and surface tension. You've got gravity pulling the fluid down, and you've got surface tension trying to pull that film to be flat. Key thing as well is that we have a fixed height. We're not fiddling about adding or subtracting fluid, so nice simple inclined plane. From that quite simple model, people can do a lot of analytical work, and you can do asymptotic analysis, and you can pull out all sorts of equations to try and describe it. And these equations, for example, Ks, which we saw was recovered before, Benny, weighted residuals, these can be quite long equations, and they can have quite different ranges of parameters for which they work. So the Reynolds number here is basically proportional to the thickness of your fluid. So as your fluid gets thicker, you have to use more and more complex equations. So basically the takeaway from this slide is there's analytical work done, there's good reduced order models that can describe how a fluid flows, but these have limited ranges of applicability. And the other idea from this slide is to kind of get an idea of what these equations look like. So you can see this H6HX, these H cubed HX, these are really similar to that library I said I was using earlier. So yeah. So why do thin film people want to use equation discovery? Well, DNS takes ages. You don't want to have to learn new DNS packages if you can avoid it. So that's why you would use a reduced order model. If you have a DNS run for 150 microns, a DNS run for 160, DNS run for 170, you might want to know what happens at 157. So if you can use equation discovery to pull out an equation that could help interpolate thicknesses nicely, that'd be brilliant. We can also use it for extensions to asymptotic analysis. So a lot of those equations, you saw just lots and lots of terms being added and added and added. And as you get more complicated, you have more terms. These PDEs can get ridiculously long. So if you were to go to the edge of where an equation might be valid, maybe you'll be able to recover a term or two that could extend a model that's derived from asymptotic analysis just to push that range of applicability just a little bit further. And it'd also be quite handy if they could recover very subtle physical effects. So for example, two solitons interacting with each other. There's some interesting stuff to do with that. So yeah, all quite far-reaching, all quite big ideas, but it's the basis of why people in the thin film community are actually interested in this kind of equation discovery. So yeah, we took the SINDy method as we did it, and we just thought, hey, what if we generate some DNS data and just chuck it at it? Because we're excited, you know, a bit short-sighted maybe, but we just wanted to chuck DNS data at it and see what happened. So we generated some DNS data, and that's the results of the DNS. So, for example, this is a point in space, just tracking the time evolution of one point in space. And you can see that the DNS data, basically, you start from a perturbed point, you get a bit of linear growth, and you get a saturated state. So yeah, gravity pulling things down, destabilizing your steady state, and then surface tension kind of keeping you from blowing up. Cool. So yeah, that's the DNS data. That's what we fed into SINDy. You can have a look at it, think about what might come out of SINDy. This, you can see a wave clearly advecting, so that's quite a strong effect. We've got a bit of saturation included, but the saturation is a very small proportion of the time. The saturation can also be seen as a bit of a steady state, so maybe there's not much more information that the saturated state gives us. Lots of things to think about. So yeah, we took that in and we just want to see what happened. And what we got back was a nonlinear advection equation. So nothing groundbreaking, nothing too exciting. But despite being simple, it was encouraging because dominant dynamics were recovered. We saw how strong that advective effect seemed to be from the DNS data. And we saw small signs of overfitting, given that the coefficient was quite small. And yeah, when we included some independent testing data, things started to break down a little bit. So that's kind of proof that whilst a fun exercise in kind of satisfying our curiosity, it wasn't anything groundbreaking on you. So yeah, and just for reference, this is what the reduced order models for that thickness of film looked like. So you can see how difficult these probably would have been to recover. You've got small parameters, you've got small coefficients and big coefficients, quite different magnitudes going on. You've got lots of terms that could look very similar to one another, particularly given thin films are working with data that's very close to a mean thickness of 1, given we're just perturbing it initially. So there's lots of things that can go wrong here. These terms, lots of collinearity, big difference in magnitudes, yeah. So it would have been difficult, but maybe one day we'll get there. So yeah, for now, we're just going to continue generating and validating on data sets of interest. We're going to work on our hyperparameter optimization routines and hopefully parallelize our optimization, because right now it's serial and takes ages. Thinking back to that advection-diffusion equation, we're going to think about the normalization of the columns and rows a bit more in the next coming weeks. And then we can think kind of more far field on, well, do we want to use soft or hard thresholding when we're trying to do our sparse regression? Currently, when we use lots of data sets, we're making sure it's the same governing PDE for each data set. What happens if we change the film thicknesses a little bit or use governing PDEs with similar but slightly different parameters or coefficients? And yeah, we want to produce reduced order models that allow for interpolation to these thicknesses. Very long-term goals there. So yeah, thanks for listening. I've got a bit quick, sorry. And yeah, that's it.